So, okay. Right, so today we're going to talk about these power law size distributions, right? So I'm going to introduce you to this madness. It's a particular kind of scaling. It's a probability kind of story. So we'll get into that and we'll try to understand how these things are built eventually, right? How they emerge in the real world and synthetic worlds. They appear all over the place. So we'll get to that. But first of all, we just need to describe it, right? We need to get our kind of mind around these things. And they're tricky. They're for various reasons, kind of unnatural. So to us. So a couple of things. I didn't quite show this the other day, but this is what these 3x2 things look like. So if you want to print them out and, well, encourage the growth of new trees. Let's put it like that. Then that's the way to go. Yeah, right. So we have this thing is working, right? So the website, there's our lecture from the other day. Blah, blah, blah. Madness. I made crazy things. And I was going to show you, well, no, I'll show you that some other time. All right, so things are popping up. Okay, so power law size distributions. Good. Right, okay. I don't think I'll get through all this particular, well, maybe, we'll see. But we'll get through the basics here today. A few little class exercises, okay. All right. Just to get your thinking working, let's turn that, just to make it easier for you to go to sleep. All right. I can work on my sleep voice if you want. Okay. Now this is very exciting. Actually, what we're getting to is the statistics of surprise, right? So it's very, you're going to sleep and then boom, right, explodes. So I'm not going to do that to you, but that's kind of the theme of this. All right. So our intuition. Oh, that's one of these irrelevant things I put in there. Anyway, that's a little joke for you later on. All right. So let's get into this. So money, right? So money is belief. Credit cards, right? I mean, we actually do say it pretty explicitly, credit, right? And it is. It's all about belief, right? It's a pretty amazing achievement, actually. I sort of think of language and money as these amazing achievements of humankind, because we've kind of, right? We don't have the gold standard anymore. There's no thing. You've got this funny little thing that says $5 on it. And actually, I think the US money of all is probably the best in this regard, because it looks like monopoly money, right? I mean, compared to many other countries which have fabulous, kind of ridiculous with holograms and they're plastic and all sorts of madness, right? But the US one says you really have to believe this is a thing. All right. Okay, so let's. So this is going to be about wealth, and I mentioned wealth the other day as being a good example of one of these skewed distributions. So I'm going to give you 2 questions, and I want you to just write things down here, and don't, so we'll talk about voting later on. You're not allowed to change your estimates, okay? Just, I'll give you a form to fill it in, no names or anything, and then I'll collate it, and I'll put up some graphs next time around. But, okay, so we're going to think about wealth into, quintiles, okay? So we're going to have 20% of people, another 20% people, another 20%, right? So 5 groups of people in the US. We're going to take the US. Broken down by wealth, and so we have the total wealth, right, the sum wealth. So how much of that sum wealth, what fraction of that wealth is owned by the top 20%, right? That's the question. And then the next 20%, next 20%, next 20%. So you have to estimate that. So you want 5 numbers that add up to 100. This sometimes can be tricky. And they should be descending, right? So in the extreme, I've got it here. All right, so what you believe, right? So I'll give you 2 things. What you think it actually is right now, or at least in the data I'm going to show you, what it is and what you think it should be. So this is where you can bring your ideology and whatever you like. No names, so no one will be, okay. So the extremes will be, you think the top 20% have all the money, right? So this is the king situation, right? This is the lord and the serfs have nothing kind of situation, 100, 0, 0, 0. Versus everyone's the same, right? It's all good. So I'm going to give you a hint. It's not these, but you have to. All right. So just write this down. So you want 2 rows of 5 numbers. They have to be descending or staying the same, and they have to be your estimates of what you really think it is and what you think it should be. Done? 1 minute. Let's do it. I mean, I'll give it to you. I'll give you paper to put on. If you have it on your computer, you can just easily. Yeah. So. Right. So that's what you think it is. All right. Here's a. Pass that around as well. And then underneath it is going to be what you think it should be, which you can go to town on. Right, 20 seconds, not long. This is not like a super question. No one gets any points for this. It's just fun. Let's just see what you think, right? Yeah. Try to be honest too, like you could be gaming it in your head, though you can do all those sorts of things. All right. But we know it's a funny kind of distribution, right? There's a Bill Gates somewhere. So we do know it's a funny distribution, but it's, now we're thinking about quintiles, so, which are weird things. So we done? We done? As long as you've got it written down and then the sheet will come around and you just translate that in. Don't look at what anyone else has done. Right, as we'll see, any kind of sequential voting where you get to see what other people have done beforehand. Very dangerous. All right, we'll see it a lot. So are we done? Have you written them down? All right, so next slide is, so this is from a study. It's Arley and Norton. So Mike Norton's at the Harvard Business School, actually. And Arley, I think, is at Duke. You may have seen, he's an economist, he's some popular, so I think, and Norton's training in psychology. So he has some popular, Arley has some books like, oh, I'm going to say it incorrectly, it's Predictably Irrational, I think. Yeah, okay, good. So this is what, they got a sample of people, like you guys here, and asked them what they thought. This is the actual breakdown, right? This is from a particular point in time. I think it's 2000, well, it was published in 2011. We could get the data. It's not, I don't have it obvious here, but it's from 2008 or 9, I guess. Okay, so this is the actual, the top 20% have 80, what is it, how much is this? 85% of the wealth, right? The next 20% have about 10% total. The next 20% have about 5%, less, 4. And then the bottom 2 are here. They're hard to see. So this doesn't mean it's a disaster. This is just pretty typical, right? If you looked at Sweden, it's going to be more this way, but it's still going to be skewed. This is the estimated, so it's off, right? So, for instance, this should be 0, basically, right? That's too much, and this guy should be here, and this one should be here. I mean, people, of course, had a reasonable idea that it's skewed. And then the ideal one is insane, right? This is almost impossible to achieve. I mean, you can say it should be like this, but it's a little hard once you get some sort of the whole money growing thing business. Anyway, this is more even than the most even countries in the world, which are the Nordic ones, I think. All right, so it's an interesting. So there's more to this. There's a couple other pieces. So maybe you can't read this. This again is the actual one at the top, and then they broke it down by people's income. And whether they voted for Bush or Kerry in the 2004 election, and male versus female. And then, so these are their estimated ones, is what they think the real one is, and this is their idealized one. So the funny thing is the biases are probably what you might guess, right? So wealthier people here tended to think it was a little more skewed, and their ideal version was a little more skewed, these top 3, right? It's a little more skewed, but not dramatically. Right? It's not like they think it should be like this. And all of them are ridiculously away from this. So this is about, people's intuition of these kinds of distributions. They're just hard to grapple with. And we'll see some other versions of this that'll make that clear. So, so men were a little, they wanted a more skewed one, but not much. So Republican versus Democrat was a little more skewed to the Republican, but not, it's not insane, right? These aren't categorically different things. This one doesn't match the ideal one. Yeah, that's weird, right? I mean, this is a weird kind of distribution, and these things are everywhere. Right, there's a video if you want to watch. I'm not going to show it, but there's a video that someone put together that's 5, 6, 7 minutes long and has lots of nice little graphics, which goes through this. Okay, so this is some plots from previous versions of you guys. And I'll make one for you as well. So this is so these are the individual ones then, and they're stacked by, ordered in a certain way. So they did pretty well. They kind of know that it's fairly skewed. The ideal version varied, right? So the economists are up the top. I think that's actually true. And so, but again, this is this very kind of relatively even spacing. I mean, the top 20 certainly has more than the bottom 10, but it's pretty skewed. And then, even more. All right, this is a better guess of the real world, but that's too much. And the ideal one, again, is this pretty skewed thing. Not everyone can get things to add up to 100. So that's why I kind of tried to say you should do that. Yeah, there's a couple more blips here. These things happen. All right. Okay. Interesting. So we're not very good at understanding what these distributions are. All right. So let's write down some mathematical descriptions of them. So, all right. So this is the business. So we're going to call them power law size distributions. It's a probability. So if we so what are we doing? So we're randomly choosing, let's think of wealth again. We're going to reach into the US and grab a human and pull them out and look at the dollar sign on them, right? And most of the time we don't get, the person doesn't have a lot of money. Very, very rarely we'll get Bill Gates and there'll be this huge dollar sign attached to it. And we'll be a bit surprised by that. But these distributions are, there's all sorts of complications here, but this is a general kind of, this is a very common kind of mathematical form for these distributions. All right, so x to the minus gamma. So we're going to have a prefactor c, and then this gamma is the exponent. We'll set it up like this. It's going to be decaying, right? So the probability that you choose something, because you're randomly choosing from the objects, that it has size x decays with x, right? So the bigger it is, the smaller its probability, right? You think about a Gaussian, it decays as e to the minus x squared. Of course, we're going both ways in that case. Exponentials, it's e to the minus x. So this is an algebraic decay. It's a power law decay. Gamma has to be greater than 1. You can think about why that is. And we'll just for the sake of argument, we'll say that it has this form. There's some minimum kind of scale, right? Now, wealth is difficult because you can have debt, of course, right? And a maximum size. And that might be instrumentation, right? So measuring earthquakes, for example, there's sort of a minimum size of earthquake that we care about or register and talk about. But of course you can measure them down to very, very small magnitudes. But there'll be typically some kind of cutoff. And then there's a cutoff at the other end, which is the whole Earth. There's sort of a size to the biggest Earth and the mantle, right? There's a size for earthquakes that it can, magnitude, the maximum size you kind of have. So we'll talk about these pieces as being cutoffs and upper cutoffs. We'll see later on you can have two regimes of scaling and you have a crossover between them. These are very typical kinds of, the words are often used in this way. So there's a cutoff to the scaling. Something that is very important but also makes a mess of people trying to make, because the thing you're interested in, we'll see, is this gamma, right? So this gamma dictates a lot about the behavior. A great deal, encodes a lot. So often it's just, what is this exponent? C is important, but this is the big deal. So if you take log 10 of both sides, which we do because we're good people, okay? Log 10. I know there's that whole natural log business, but we're good people, okay? Orders of magnitude is where we work. Not just to talk to engineers, but this is just, I don't know, you can look at your hands, it's fine. But this is where orders of magnitude. So log 10 of the left-hand side, and we get this nice separation on the right, log 10 of C minus gamma log 10 of X. So it's a linear, on a log-log scale, on a double logarithmic plot, it's going to be a linear, if it's a perfect power law, it's going to be a linear function. So that seems good. You can go and, all right, just do a regression, right? You guys have learned about that probably, right? Some horrible thing happened to you in calculus, and then maybe in linear algebra was much, much better. You can measure the regression, right? You can carry out a regression, get this exponent. Lots of arguing about that, how to do that well. So these things happen a lot in probability distributions. I'm going to call it statistics of surprise. And how surprising depends on gamma. So it's often true that this is just for the tail, right? What we'll call the tail of the distribution. There's something happening at the front of it, and then it decays. So that's true too, okay? And we can have explicit kinds of distributions that actually, the mathematical ones that have a nice tail. There's inverse Gaussians, there's all sorts of things that have natural reasons for being. We'll talk about still being a power law size distribution, even if it's just a tail, okay? Fine. Sometimes you'll hear people, doesn't sound right, but fat tail distributions, heavy tail distributions. The point is there's some stuff out in the tail, which is, I'm going to show you a plot in a little bit, which is a bit surprising because when you look at the plot, you might not see that. Whereas exponentials and Gaussians and those kinds of things, they don't have big tails. Right? They have tiny tails. Now, so this from the start, there are lots of other things that could masquerade as pure power laws. Log normals, incredibly common distribution, right? So we'll get to this later on. It's something that appears because of very natural kinds of growth mechanisms, and certainly is observed in the real world a lot. Weibel distributions are all sorts of other little sneaky things that have their own generative stories. Now, those aside, there are many different generative stories for why these things come about. And I'll sort of repeat this, but so the central limit theorem for the normal, the Gaussian, the bell curve, that's this one beautiful story, right? And there are different ways to prove it and so on, but it's this one story. But there are many stories that get to these things. And so there's arguments about measuring it exactly and saying, oh, it really is a power law versus this. And once you've kind of had that argument, then there's, well, how did it come to be? And here's my beautiful theory versus your beautiful theory. So you have to get into the mechanics of the growth of the thing. All right, so we'll see these things appear a lot. Couple of examples. So we can do it for, well, first of all, that was set up as a continuous variable, x. We can certainly do it again for discrete things. So something where you're measuring numbers. So word frequency, that's a simple, interesting, fun thing to do with language. So you get hold of Moby Dick, try to read it, but it's hard. It's symbolic for the, well, that's a Colbert joke actually, right? That it's symbolic for the struggle that is reading Moby Dick. Anyway, so yeah, which you realize about page 40. The vestibule gets described for 3 pages. All right. Okay, word frequency. So that turns out to have this, right? We don't have some kind of funny other, we do have these long tail distributions. There's all sorts of, that's something we're still arguing about. 65 years of one of our students has done made some great advances there, but that's a 65-year-old observation. We'll come to that later on. There's a fellow called Zipf. So no degrees in networks. Now, not really actual social networks where you talk to the humans. When we say humans, we're bad people. Okay, so that's always, I'm joking. But where the people are actually talking with each other in real space. But certainly this can happen on social media and so on, where someone is being followed, so Lady Gaga has, I don't know how many it is, 20 million, some enormous number of followers. But they don't reply to them all, right? Of course, they can't do that. So, but in that kind of space, you can get these runaway distributions. And so you might see that. So you count the number of friends. And then you might wonder, well, good friends and all these sorts of things. But if you just simply look at the network, count the number of friends. If you look at the web, one of the early observations of these large-scale networks was for the web. And as it was growing, of course, it was relatively like this little baby web. This is 1998, 99, and we'll come to that later on. Same kind of thing. You see that sort of distribution. If you look in citations, so you can look in academic literature, which you probably don't want to do, but if you can look in court decisions, so Supreme Court decisions, and so on, you can see these. You can count the number of times a decision counted, how many citations it made to previous decisions, and then you can look further down, right? Okay. I mean, this is all underneath Google and all sorts of things. Okay, so we still say the same sort of thing. We have, now it's a discrete variable. It still has the same formalism, right? Obviously, you can't do it for k equals 0. There's some, so now it's probably 1 is a very natural lower cutoff, right? A word that appears once in a book, or have one friend. So if you have 0 friends, then this scaling has to kind of go off a little bit. What's a word that appears once in a written work? There's ridiculously a word for this, right? So it's hapax legomena. It's great, yeah. Then there's one for words that appear twice. Anyway, very enjoyable. It's Greek, madness. So this is a particular, this is an old one actually, Brown Corpus. It's a compilation of all sorts of written, I think, maybe spoken as well. But this is the ordering. So the, of, and, to, a, right? So you've got your function words lined up at the start. And these are the fraction, so close, in this one at least, close to 7%. Typically it's sort of 4% for the, but it's clearly dominating. We get out to, say, the 2000s here, and we've dropped tremendously. So I'll show you, there's a visualization of this that was put together by Jonathan Harris, who we've had up here as a artist in residence. And you really just should, if you haven't seen this guy's stuff, you should just look at his work in general. So this is an old thing of his, but it's kind of fun. So you can just scoot around. It's got, how many words are in here? I think there are, close to 90,000. So it has this nice little, right? So now we're at motility, ton, which of course is for people from funny places. Who'd like to hang on to some extra letters in there. I mean, U in color, it's fine. Rescuing, attractively, right? So then you get out to some funny things. So you can just play around in there. You can look for words. So here's a sneaky thing he did, right? You can look for words. All right, so imagine which words you might look for. I'm not going to show you what people look for, but you can go and look later on, okay? It's not great. Let me just say that. It's not great. But he kind of captured that on the back end and then presents that as another little, thank you, people. And I think there is a fun thing in here. Right, so that's query count. So these are the words that people, so not touching that. And then this is a fun little bit. So these are apparently, that's hard to say, isn't it? Apparently conspiratorial, well, it's not good either, but these are words that just appear in order. This is like Bible code stuff. Apple formula, imagination, put the colon in, just a temple plot, establishing courage. Toucan tonsillectomy, I guess is just fun to say. Mathematics, fool, specially brush inspection, lad. Anyway, so people started to send these into him. Anyway, that's just for fun. Oh yeah, there's a lot. Wow, okay, yeah, okay. Arafat, unhealthy. Yeah. So, all right, so he had some fun with that. But it's a perfect visualization of this business. Okay, good. Yeah. So that's way out there. This is 55,000, Spitsbergen and turboprop. Cool. So words are fun. Yeah. And so out here, they're all the same, right? Once you're out here in this part out here, the probability of them, all the ones that are adjacent to each other, they're all the same, right? This is a tiny bit lower than this one. There's a big drop off at the start, right? We get out to here and they've just evaporated in probability. And the scaling here may be not linear either. Anyway, all right. So we've mentioned, so they're just a couple of examples. I like words, so they're always fun to play with. I'll give you some more. I'll give you a whole batch at some point here. So where did I put this thing? Yeah, good. So, right, crazy thing. Gaussian, we've got a pi in there. I mean, it's all this amazing, beautiful stuff. This guy appears everywhere, so here's a typical one. We talked about the log-log thing, right? So this is what Gaussian looks like on log-log. And I did a sneaky thing by putting an average around 10, of course, because log only works for positive numbers. So like real world stuff. Okay, so that's how that thing gets transformed. You can still see it's got a peak in it. You can still see that there's a characteristic scale. So this is a word we'll say now over and over, that there is these kinds of well, I won't say those words yet, but there's a Gaussians and exponentials and all these other very common distributions. There's a characteristic scale, right? There's a mean, there's some parameter in there that is typical of it, right? So if this was heights of people, 10 somehow is, whatever it is, 5'10". Let's say we're in Denmark at 6'4". And, there's some normal distribution around the height. That's fair enough. Yeah, you'll see that. Okay, so there you go. So here's another quick little thing to sketch, or at least create it in your brain. So Q equals 1 to 10 to the 6. I need to change those numbers. Okay, but let's just say it's 1 to 1 million. So you're just plotting 1 to a million, Q to the minus 2. So just draw that for yourselves. What does that look like? right? You go to sketching graphs, right? Okay? This is 1 to 10 to the 6, when no 0. You have that? Q to the minus 2? Not using a... Okay, all right. I thought you were using... No, let us say that word. Okay, so that's what it looks like, right? It's... So that's a weird looking thing. So you would think, oh, it's always going to be this. Like if this is a probability distribution, it's always going to be this guy, right? It's going to be small. When you sample from this thing, probability of getting any of these things out here is tiny. Q to the minus 2, or let's say k to the minus 2, which I'll change it to k. That kind of distribution is actually a pretty horrible distribution. It's on the edge of having an infinite mean. So this distribution is on the edge of having an infinite mean. Where it's pretty, when you look at this in linear space, you think that's insane, right? So no one ever plots this. They never plot this because it's completely uninformative. So you take the logs of both sides, and this is what you get. This is actually for the Brown corpus, for the word distribution. And all right, it's not bad. It's got this fairly linear structure here, and then it gets a little wobbly because now we're out at here at the words that appear with high probability, right? So this is the probability they appear. So that's the and of, and there's only one of them, right? This is the count for them. There's only one of those guys. This is log 10 of 1 is 0. But there are lots of ones that appear. These are the hapax legomena. These are the words that appear once. There's a whole bunch of those. So it's a very interesting thing, right? So you can think of, say, also like, say, diseases, right? So they're very common diseases that we all know about, like cancer and so on. And then there are all the rare diseases, which can be connected by the fact that they're rare, right? So if you have a mechanism for solving rare but very different ones, then you'll actually contribute a lot. And another version of that is to say that the people who don't have much money, taken collectively, add up to something, right? Their wealth adds up to something, or should. The is sort of this big thing. If you just take your book, you take Moby Dick, and you've really enjoyed reading it, but now you just tear it all up and you like sift all the words out. Thank you, Herman. Then you'll have a whole bunch of these. The pile will be huge, right? Yeah. And there'll be a lot of whale, a lot of Moby, harpoon, stuff like that. There'll be a little Nantucket pile, Queequeg, all that sort of thing. Actually, there really are some fantastic words in there. That's true. When you go out and find those rare ones, there's some ridiculous things, like with 3 hyphens. Anyway, so okay, so this is very strange. This is on the edge of having an infinite mean. If it kept going, if it was an endless book. Okay, so that's not. You can see this is a little bit messy. We want to fit a regression to this. We're going to put a straight line through this. That's going to be a little bit messy. So we're trying to cope with these beasts. There's a lot more we have to get out of these things, but it's just a start. So this is what we'll call the exceedance probability, or I'm going to call it the complementary cumulative distribution. It's got a couple of names. So cumulative distribution, right? So probably that the thing you've sampled is less than some value, right? Normal sort of thing. Complementary cumulative is the probability that it's greater than something. So I'm going to write as this n greater than q. I want to change these things. Could be greater than or equal to q. And that's an integral, right? You're integrating, right? So you're taking this thing, and instead of this point here, you're saying, all right, we're going to add all of these numbers up and put that in there, right? So we're integrating this way. So that cleans things up because it has to grow, right? The number of words that appear a certain fraction in the book as you go back in fraction, like this. So eventually you get to the smallest fraction, which is this is 1 over n, where n is the total number of words in the book. Then you've got every word, right? The probability that a word appears at least once in a book is 1, if you're looking at all the words. So this thing is an integral, and we'll look at this a little bit, and it's generally speaking, it's cleaned up. You can measure this exponent and connect it back to the underlying one. And there are arguments about doing this, but it seems to be the right thing to do. Okay, little fun thing as well. We're not going to do it really, but I have done this in class. But you can, right, so based on what we just saw with Jonathan Harris's thing, so if you want to test someone's vocab, that's hard, right? You have to ask them, please, do you know the 60,000 words? Sit down. Yes, no. And be honest. And here's a camelback or something. Right. So one way to think about this is, well, let's look at different parts of the distribution. Ask some relatively easy ones, and depending on how well they go there, you can think about scaling out. Right. So if you want to do it collectively, okay, we're going to do this. Well, let's just see. We'll just set it up. Yeah. All right. So you go through and you say, okay, which ones do you know? So we should know all of these words. All of these words. We're happy with all of these words. Streamline, yes? 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 Discomfit? Yes? Sedulous? That is a funny word, yeah. What about these ones? Vibrissae. You know at UVM, right, we have Jacques Bailey, right? We have the guy who asked the questions on the spelling bee. So we're killing the bee, which I'm sure you've never seen. But if you see that movie, he's in it. He's a professor of classics here. And yeah, he won it in 1981 or 2 with elucubrate, which means to study late into the night. It's to do with lamp oil. Oxyuricide, that's going to be murder of wife or spouse, if I can spell it correctly. Oh, no, I've lost it. Side. Bad word. Wife specific, that's bad. Sedulous, that's all bad. Sedulous is terrible. So this is a word that doesn't sound like what it means, I think. Showing dedication and diligence. Just doesn't, right? It's like a pulchritude, which means beautiful. Terrible word. I mean, if you said someone looked pulchritudinous, they'd probably punch you in the head. Vibrissae is whiskers. All right, so we sit here, and so you'd say, yes, I know these, and I'm totally all over this one. Right? And then it would show you a whole bunch more, and we can't do that. But then it gives you an estimate of your vocabulary, which I got Jacques to do, and his is like 45,000 or something. So anyway, so that's a sneaky little fun thing. Again, to do with words, but sort of definitely capitalizing on this business. Okay. So you could do that later on if you want, if you behave incredibly honestly and so you don't really know what sedulous means. Yeah, see, it just doesn't sound right. So, like, an onomatopoeic, maybe. All right, so lots of others. I'll give you a little grab bag now. So we've talked about earthquakes. This is the very famous Gutenberg Richter law. It does have some different regimes of scaling. This one I've taken from oddly, a paper that was published in 2 places at the same time, which was kind of an awkward moment. One was in the Proceedings of the National Academy of Sciences, and I think there was some, a bit of a disaster. I think they thought it was a colloquium paper, and I think the idea was, we can publish anything we want, including this paper that we published in Physical Review Letters. So a bit awkward, but they changed the author list. So I don't know what happened. Anyway, so this is real. Okay, so this is a big deal, right? I mean, so this is actually, it's an awful thing, earthquakes, right? So this is from 2011. Well, there's this, the fact that Japan and the US got moved and messed around with the Earth spin, obviously, small amounts. But so this is something we'll talk about with these. That's a statistic of surprise. So how misleading history is the statement here. So 300 years there'd been nothing like that in Japan. So this is this horrible earthquake causing a tsunami off of Japan. Hadn't been above magnitude 8. So quite, it's not. We do know about these things now, so you can't get into a complacency with them. From what I understand, there were stones put into the ground at different points, sticking out, kind of well, not as big as Stonehenge type things, but saying do not build beyond this point, right? And so hundreds and hundreds of years go by, and of course you start to build beyond because maybe the sea doesn't do that anymore. And they were from the 1300s. But we do talk about a 100-year flood, 1,000-year flood. We get confused about those things because 100-year floods come every 3 years, right? But we're trying to grapple with this very uneven kind of distribution of things. All right, so it was a disaster, right? So most people by this point most scientists didn't think this could happen. And I don't have it here, but we did talk about the Italian scientists who were arrested and I think now imprisoned for underestimating the potential impact of an earthquake. People remember this? Did we talk about it? Yeah, okay, yeah. Okay, so these distributions are weird, and I've said this before, but in general, we're terrible with probability, right? So I won't discuss it here, but the Monty Hall problem is a classic, right? This is the shell game. So you know about this one, right? So it's a classic one, right? So the Monty Hall game is something, but there's a something under it, whatever it is, a rubber chicken under a cup, and you've got 3 of them, and they're messing around with it, right? And you have to guess. And so you guess one of them, and then the person playing with you will say, all right, it's not under this one, the one you didn't guess. Do you want to change? Do you want to change your bet? And that's the question. And the intuition is that it shouldn't matter, right? That's the natural intuition. Lots of people get very upset about, we do understand it now. It's generally known about, people know about it, but at the time, you had professors of statistics and so on writing to puzzle makers around and saying, you guys are idiots, it's clearly what we think, and they were wrong. Okay, so I'm going to show you another fun one here to think about. I will go through it quickly, but you can think about this. It's the so-called daughter or son born on a Tuesday problem. This is another piece you could listen to later on if you want. It's about 10 minutes long, I think. But it's the idea, and we'll get to benefits a little bit, don't worry about that. It's on numbers, and there's some, part of that is about how when infants are reasonably good at estimating orders of magnitude. So 100 and 10 and 1 sort of seem to be evenly spaced. Of course, we've got logarithmic stuff all through our bodies, right? Our listening and so on. But it's something we kind of beat out of ourselves, like, all right, you're going to count to 100, right? 1, 2, 3, 4, and then we sort of lose the ability in a way. That's the notion here, to think logarithmically. And you should think logarithmically. It's good. All right. And there's some other pieces in there. So also in groups of people that have fairly primitive languages where there isn't a number system, right? They're not counting. They don't have a counting thing. Then you also see this idea that 1 and 3 and 10 are kind of evenly spaced. Like 3 is in between 1 and 10. Like that's halfway between 1 and 10, which logarithmically it is. All right. So here's a little thing to think about, and then we'll go back to the story. But this is just about our terribleness with probability. So we have a parent who has 2 children. Okay, just 2 children. I think I can say they're not twins. And so, okay. Yeah. So simple question. So what's the probability that both of them are girls? And we assume that the chance of having a girl boy is 50-50. 51 point. What is it? It's a quarter, right? So that's totally quarter. We've got that. So we've got a quarter. So what if we have, so another parent has 2 children. You know they have 2 children, and then one of them is a girl. You know one of them is a girl. So what's the probability that they have, that parent has 2 girls? Slightly. Half? Okay, so this is a quarter. This is a third. So this is already bad, right? It's going to get worse on the next one. So you know one of them is a girl. So it could be. So let's think about so they could have a girl then a boy, or a boy then a girl, or the girl then a girl. So there are these 3 even things, and 1 out of those 3 is the girl. So that it's an order thing. So that's already upsetting. It's fine, you should be upset. I think you should be upset. Right, so just think about the history. So we've taken a random parent, and they have their 2 kids, and we get to hear that they have one of them is a girl. We don't know which one is, the older one or the younger one. Right. So it could be a girl and then a girl, boy, then a girl, or girl and a boy. So it means a third of that population will have 2 girls. Okay, so we're terrible. All right. You're good people. I mean, the thing is, you think in the right way. You tell stories. You survive. You don't get eaten by tigers and things. That's all right, right? You have lots of systems in here that generally, yeah. I mean, obviously it goes wrong, but this is just not something that evolution gave us, I think. Right? Okay. So all right. So a parent has 2 children, and we know one of them is a girl born on a Tuesday. What does that do? So what is it now? What's the probability that they have 2 girls? You're trying to, all right, the week is good. The 7th, there's a 7th floating around. Good, yeah. Okay. Would you think it should matter? Does it feel like it should matter? Right, good. So that's the right answer. Okay, so you're humans. That's good. Right, people. It should not matter. And actually, I think this is a recently kind of spread around puzzle. Right. Someone asked it at a conference somewhere, and everyone's like, they're all people with giant brains, and then the audience, they're like, we're all very smart. I'm like, no, it doesn't matter. And they're yelling at each other. It totally matters. So this looks like the previous question, right? We knew one was a girl. That moved it from a quarter to a third. This will move it again, it turns out, even if it's very unsettling. And then what if we know one of them was born on December 31st? What does that do? Yeah, and let's say there are only 365 days, which is a whole calendrical nightmare, obviously, right? Yeah. So you think about that one as well. But what's a great challenge? If you can sort this out, then if you can figure out what's a good way to explain it clearly and easily, in a way that may help you in another circumstance, that would be an achievement. Okay, so what's probably both of them there? Okay, question marks. All right, you can think about that. Okay, all right, so we're terrible at probably. Okay, so lots of other examples, and I'm just going to give you a couple more. This appeared last year, so it's looking at the ingredients, right? So now we have, of course, all this data online, and so there have been a number of interesting papers that appeared recently about recipes. And so you can see lots of different, so there's sort of a general, whether foods are paired as opposites or they're matching, so the opposites is more of the Asian cuisine and Western cuisine is more matching. And you can see that in recipes, nicely playing out. People have looked at not just the ingredients, but then the constituents of those. So this is, the number of ingredients appearing in the number of, in K recipes. So you have some things that appear everywhere, like salt and so on, and then you have the more obscure ones. But it follows one of these parallel things again, right? That's the story. So this is a paper you might want to dig into by Mark Newman, who we will talk about a fair bit. He's a huge character in complex systems and particularly complex networks. He's one of the big characters at Michigan. Spent a lot of time in Santa Fe. He's English, but what can you do? Okay. He escaped. Okay, so all right, I got to say that. Yeah. Okay. Yeah. Let's see. Okay, so it's all about power laws. We'll see this word Pareto, Zipf's law. We'll see those in a little bit. So here's just one plot. And now we're going to look at other things. So of course he has the word frequency, and I'm sure it's Moby Dick. Is it Moby Dick? Yeah, it's Moby Dick. Everyone does Moby Dick. Citations, and this will be in papers. So web hits, how many times web pages hit, those sorts of things. This is books sold. Again, so these are all log scales. Calls received, so particular numbers receive many more, which makes, so Of course, this is something that wouldn't work for individuals that's sitting at home, right? Because you couldn't have this skew. No one's going to get that many. These will be going into hospitals or bigger institutions, whatever it is. Yeah, so it gets beyond this is earthquake magnitude, intensity of, what's that one? That is, actually this is good. So this is crater diameter on the moon. So of course, some say, what are the measure, count them all up. I think that's solar flares, peak intensity of solar flares. So we're talking about a lot of different things, is part of it. Yeah, gamma ray intensity of solar flares. These are, okay, this is very famous. So this is wars, and in fact, the last work that we have connected to this that's recently, appeared, that's come out of this course is actually to do with this kind of this work. So it's Richardson, very, very famous guy. I'll link to some of his stuff. Famous from the last century. He has a name in fluid mechanics, constant in fluid mechanics named after him. And so he actually predicted weather prediction in the way that we do it. He said, we're going to have rooms full of people calculating differential equations and maybe these computer things. But this is in the 1920s. And he also thought about war, which he called deadly quarrels. But it actually went from, I've got the book, if anyone's interested, it's very fun. But it goes up from like double homicides to wars. So the First World War and Second World War. But the magnitude of these things seems to follow something like this. And that's true for terrorist attacks as well. And there are arguments for why that can be, how that can be explained in a generative way. Meaning, groups kind of coalescing and coming apart and so on. So this is wealth, name frequency. And this varies a lot depending on culture. So Korean, for example, doesn't, if you look at last names, does not have this structure, for example. City population. And you can see, what's happening, right? So he's indicated here that the fit isn't very good here, and it's broken away. It's really about the tail. And then some of these, one can argue. One could say maybe it's a log normal or something, and there's a reason for that. But generally speaking, they are all certainly heavy tail distributions, right? These are orders of magnitude here. That's actually not many. That's one order of magnitude. 6 here, 5 here. I will say it later on, but 3 orders of magnitude in both axes is good. If you have good scaling over that, then that's okay. You do see some shaky things. All right, these are just lists of them. Sizes of forest fires. These are to give you just some of the exponents and so on. There's another paper, so we'll come to Simon later on. Newman also has this paper with Clauset and Scholese for more about this stuff. And this is one, it's become I guess it's an outlier itself. It's got like 3,000 citations or something now. So it's a way of, kind of a somewhat difficult way, but a way of measuring these exponents, which everyone gets upset about. Lots of things. I think I've said all of these. Tree trunk diameters, that's fun, right? So one of our papers was trying to figure out how this works, right? So there's what's it called? There's sort of a standardized height that you figure out where it is on you. Yeah, right? Yeah, diameter of breast height, DBH. Right, so you figure out where it is on you, and then you go out to your tree and you say, okay, this tree. And trees are really good because they don't run away. It's much better than the animal things. So you can count them, and you can see where they are if they're getting bigger, right? So that's actually, if you're interested in that, we could talk about that. Because they do seem to follow this a distribution, and you can think about how things fit together. It's very nice, connects to all this beautiful old math about Apollonian packing and so on. This is a little one. We'll compute this just for fun later on. So-called Holtzmark distribution. But if you randomly relocate yourself to somewhere in the universe, which is, a bit of an ask, then probably that the gravitational field there will be F. Decays as F to the -5 halves. And -5 halves, so it's between 2 and 3. That's in this, as we'll see, that's in a very interesting value of this exponent gamma, which I'll call it general gamma, where you have, and we'll come to it, but where you have a finite mean, so most of the time, lots of small things, but an infinite variance. So it's the great example of surprise. You keep sampling, like, there's nothing going on, and then suddenly you're in a sun. That's bad. So sort of a Doctor Who shout out there. Okay. Lots of things. Sightings of birds per species. Yeah, right. Birders are totally into this. Yeah. And they're really good at, well, they're pretty good, right? And I'm sure with the apps now, people must be really great. Yeah, right? Oh, that's super interesting. Oh, I'd love to talk about that. The snowy owls were good, right? Just a couple of years ago, because they went straight up. Yeah. Yeah. Super interesting. Oh, religious adherence to cults. Awesome, right? Interesting paper. I wonder if the cult might be, I hope it might include the big religions, so they might get in a lot of trouble for that. But it's hard, because it's the same with the war thing, right? So deadly quarrels, right? So that, because they're trying to have double homicide all the way to Europe exploding again, right? It's hard to get the right word. Okay. More. There's lots of them. Okay. Let's see. Any more fun ones in there? But I think that's pretty good. But you can see, yes. Oh, size of blackouts. Yeah. That's a good one. Right. Yeah. Most of the time, it's just your light bulb went off in your basement. That's a blackout. It's not included, but it is a kind of a blackout. Well, your street goes out. Lots of little ones like that, and now and then it explodes. This is a famous book, and it tackles famous. Yeah, I guess so. So-called Black Swan story. Bit funny. Okay, so this is tries to sort of frame it as the normal distribution of the Mediocristan, and the power law ones are Extremistan. Has a little bit of fun with it, but this is sold tremendously, and it's absolutely true in the financial world that the difference between those two kinds of distributions has certainly not been appreciated in certain areas, and has led to massive failures of things. Long-term capital was this great example where they had an 8 sigma event, right? So if you're saying it's Gaussian, if that's what you really think it is, and then you measure the events, it's an 8 sigma event. That should never happen, right, in the universe. But you should stop calling it an 8 sigma event, because that's not what it is. You've got the wrong distribution, right? So the black swan, that terminology comes from, so it's a surprise, and the idea is it comes from actually Western Australia, where there are black swans, right? So there are white swans everywhere in the world, and then some random Europeans, probably the Dutch, find themselves wandering around in what they call New Holland, and they found these black swans. Now, I don't think it's actually a good label, because that's sort of surprising, but it's still a swan. Like if it was a swan that talked to you, and was incredibly good at basketball, I don't know, that would be really surprising. So anyway, it's become a term that no one probably understands, but it's become a term, and now you have companies where it's like, I'm going to find 7 black swans today. Like the point is you're not supposed to find them. But you should expect, it's how you characterize the world, okay. Height versus wealth. So, he has some fun examples. So this is the weight of a turkey. This is how long it's lived for about 3 years. So the history doesn't inform what's going to happen tomorrow piece. Just as we saw, yeah. It doesn't weigh anything, yeah. Okay, so and that's a thing that he hammers on. And it's true. So if you have something that has normal, sort of a normal distribution, you get lots of samples and it starts to fill in, you're like, okay, that's what this is going to be. But if it's a power law, you sample for 100 times the time scale you've already used, and then 10 times that time scale, 10 times, you'll still keep getting bigger and bigger things. So, and you're always like, I don't know, is this going to stop, right? What's the most wealthy person in the US? What's the biggest earthquake we could get? So if you have a very small sample of California's, like 3 months of California, it's really going to matter when you took those 3 months. If you really believe that's indicative of the whole thing, then you're in a lot of trouble. He has some silly things, right? So the most typical member, this is good though, I suppose, member is mediocre if it's in this mediocre sense, so the normal distributions. Typical ones are either giant or tiny, which is true. Right? This is a word, and we'll say it again, so this is to do with this, whether the distribution has a scale, right? Has in a scale. The winners get a small segment, right? So the ones that have the most wealth, if it was a normal distribution, would have a small segment. The winner takes much more, all perhaps. You know, you can think of the web, right? Google has a lot more links coming into it, hits coming into it than my website. And again, this is the story. You observe things for a while. You absolutely can characterize it well. It takes an incredibly long time, and you can still be surprised in this other case. Prediction is easy. Prediction is hard. But of course, you know, where we can do this, totally fine. But history crawls. History makes jumps. Tyranny of the collective. Tyranny of the rare. Okay, not bad. So he has some fun. You'll see this as well. So Pareto economists will use it in this way, but you'll see this in physics as well. People will talk about Pareto distributions. So it's one of the first observations of these power law size distributions. It was for wealth in Italy. It's the late 1800s. And so he came up with this one. So we're talking about a distribution of wealth, right? So wealth is here, and then there's the frequency. We'll tackle this later on. So the 80-20 rule, which has been incredibly popularized recently. So this is the idea that 80% of the people have 20% of wealth, 20% of the people have 80% of the wealth. That's just one point, right? Does that mean that 75 have 20? It doesn't actually, right? So you have to think about that as well. So this is a useful distillation, right? There are other things like Gini coefficients and other kinds of words that people transfer. They take this whole distribution and put it into one number, which is sort of a predilection of people, right? We'd like to have even things like effective temperature, which somehow contains rain and humidity and temperature. You know, it's okay, but we should be able to handle more numbers. So the thing that, of course, is recent is 99%, the 1%ers, that idea, right? So that is trying to capture this, but it doesn't quite say it, right? So it doesn't mean that 99% of the people have 1% of the wealth, and that sort of gets lost. It just sort of says there's 1% and there's another 99%. Yeah, right. I don't think it sort of has, as that thing is spread around, it doesn't quite have what the 1% have, like exactly what it is. It's 99 point something. Anyway, all right. The dismal science, all right, economics, which I always thought meant that it's a bad science, but it didn't. It actually means that it was a study of dismal things about humans. Okay. All right. Okay, good. So let's get back to some of these horrible details. I've sort of mentioned some of these things, but let's take our definition. We'll take it exact. We'll say it's c to the x minus gamma, and we'll say there's some minimum and some maximum. That's fixed. You can calculate this. This will be a little, just a little bit of. It's an integral. It's not a bad thing to do. So this is the way I like to write averages. A little bit of a physics thing, I guess. This little bra and cat, these guys. So the average value of x, if you compute this, you go through and find the mean of this guy. So you get this prefactor sitting up here. You get a 2 minus gamma sitting here. So that's why we had to say gamma not equal to 2, because we'd have to treat that slightly differently. And we get a different result. X to the 2 minus gamma and x min 2 minus gamma. So the n scales appear. Right? The exponent is here, the prefactor is here, and then the n's appear. So there's no inner scale that's popping out, which is, if we did this for the Gaussian, right, we get mu, if we've defined it in that, we get a characteristic scale. So there's no characteristic inner scale, and that's an important thing to think about. Okay, so what happens, and x min is maybe, a million times bigger than x max is a million times bigger than x min, right? Or 10 million, 100 million. Huge scales we're talking about. So if gamma is less than 2, the mean blows up. So if gamma is less than 2, there's 2 minus gamma, right? So you guys have to figure out how to get here. But if, let's say it's 3 halves, right? So we get x max to the half. Then the bigger x max is, the bigger this thing is. So it's actually being governed by the upper limit. Right? So that's this. Your typical sample is a giant, right? You're sampling from this thing. You're actually getting big. But it still looks on a linear plot, it looks like this, right? It's very disconcerting. But when you're sampling from that kind of distribution, so if gamma is 3 halves, then most of your things will be big. And it's still, it will, so, all right. So think about this. If now if gamma is greater than 2, then let's take 5 halves, then we have, So let's take 5 halves, then we've got x max to the minus a half, right? I can add small numbers together. X max to the minus a half. So, right, so it's 1 over x max to the half. So that thing is going to be really small, right? Some giant x max is going to be really small. And then this one will pop up, right? This negative sign will flop with this guy because we'll have a minus a half here, we'll have minus a half here. X min is a small thing. It gets to dominate. Right, so this guy will evaporate, and we'll see that the typical sample, so this is the thing, so the typical sample is large if gamma is less than 2, and small if gamma is greater than 2. So this is just the first, it's just the mean, but it depends entirely on, well, not entirely, but it depends primarily first on gamma as to sort of its nature, and then it will be connected to the minimum or the maximum scale, these cutoffs. Okay. So we get some sense of these things. So we can get the moments of the distribution, right? So that's the average of x to the n. Right? If you have all the moments, you can reconstruct your probability distribution. These are very basic things. And if if you're not aware of them, we can talk about it. But certainly something to look up and think about. So all the moments depend only on the cutoffs, and of course just gamma and so on, but there's no internal scale, right? There isn't an internal scale, and I've talked about this. And for many real distributions, and we had all those examples, gamma is between 2 and 3, and these are statistics of surprise. This is that land of statistics of surprise. The mean is finite, means it's nice and small. It depends on the lower cutoff. Most of your samples are small, but the variance is, in a sense, infinite, right? So it's governed by x max. It gets bigger and bigger and bigger. That's not computed here. This is another question for you guys. And you can talk, so the width, we talk about width, variance, 2 times the standard deviation. That's the width of the thing, right? So a Gaussian, very, you specify it with your variance, but it's a nice constrained thing. So this is in principle infinite. And if gamma is greater than 3, right? So that means, so gamma greater than 3 means your slope is like this now, right? Because it's to the negative gamma. So it's like this on the log-logs plot. So the tail isn't as fat, right? There's not as much tail. It's down here. So the variance is as big, and in fact the variance is not, now it's tied to the minimum cutoff, the small cutoff. Right? So you see that the higher order statistics, you can look at the x cubed, right, or x to the 4th and so on. Things like skewness and so on, those things that depend on these higher moments, they will still be infinite, and things clock as you go up through the moment. But anyway, this is words, stop words. So gamma greater than 3, things start to calm down. Right? You have a finite mean, your variance is finite, you're not going to see giant things that much, but it's in here that they get the bad things. Well, this is just a little piece about standard deviation. It's a bit of a funny thing. It's nice analytically, right? We do this x minus mu all squared. Right? We want to find the average of this. This is the variance of x. It's a nice thing to work with. So, for instance, the normal distribution, the Gaussian, we can compute it exactly. Very nice. But if you're thinking about what's the width of this thing, what's the typical? So you've got your average. What's the typical? If you sample many, many times, how far away from that average will you typically be? You might actually want to do this, right? Which is just what's the average absolute distance? Analytically, this is a nasty little beast. But it does have different behavior in terms of whether it explodes or not. And so, as I said, the variance explodes. So it becomes very, very large when gamma is between 2 and 3. But this is actually finite. This is not so horrible. So you don't have to worry about this too much. So it's a mean average deviation, MAD. But it's a nasty thing to do with. Okay. So we'll still talk about something having an infinite width if gamma is between 2 and 3, because it's really about this variance measurement. where variance is, defined in this particular way that we've statistically. Oh, I think. This is an interesting piece. So we talked about how, right, so if you sample from a normal distribution eventually and you put all your little guys in there, you'll start to see it fill in, right? You will slowly, over time, you will get a bigger one than you've ever seen before, or one that's more negative or one that's more positive than you've ever seen before. That's true, but it will grow very, very slowly. Bit of a hard thing to compute, but you can. There's a beautiful area of statistics called extremal statistics, which is about that, right? So what's the largest guy going to be after n samples typically? So you can compute this. What's the expected size? This is a nice little calculation. A couple of steps to it. What's the expected size of the largest sample after n samples? And so here's the number of samples. So you expect it to be on the order of or greater than. There's some coefficient here, but n to the 1 over gamma minus 1. So what does that mean? So gamma is always greater than 1. There's a reason for that. You'll get to. So this is always an n to some power. So it's always growing. So for instance, the gamma equals 2, which is that nasty point where you go from a finite mean to an infinite mean. You've got n to the 1. 1 over 2 minus 1. So you've got n to the 1. So the maximum guy is actually growing linearly. Right? You're sampling from, if this is your earthquake distribution or your financial collapse distribution or wealth distribution, you're sampling away and you're regularly getting someone who's bigger and bigger and bigger. If it's, say, at this other edge, 3, so that's end of the half, right? So it's growing, it's still growing, it's rolling over, but you're always getting bigger and bigger things. Much slower growth if you sample from any of these other finite variance things. So this is just a standard exponential, lambda e to the minus lambda x. You can figure out that this is how it grows, right? So it grows logarithmically, which is slower than any algebraic thing. It's just struggling. Basically, it's not growing. All right, that's a good little assignment question as well. Okay, so the thing that I called exceedance probability. So let's just start this off. I'm going to connect it to what's called Zipf's law. There's been some confusion about this over the years, but it's sort of clear in the last 15 years that all people more widely known that these things are all connected. So let's get these guys to work. Just do a little calculation and then that might be a good place to stop. All right. So I'm going to write it in this way. So this is the probability that your sample is greater than or equal to x. Okay? Yeah. So it's going to be an integral. So this is writing out more fully. So it's 1 minus the probability that, and this is the normal cumulative, shouldn't say normal too much, cumulative distribution. So it's 1 minus the probability that x prime is less than x. And in terms of integrals, it's pretty straightforward, right? So it's just the integral from x to infinity of your probability. What is underneath the, right? So if we had our Gaussian, right, we're just going to integrate here and find out how much error is here. And with our ridiculous guy that actually looks like this, we're going to find what's out here. And of course, we always look at it on a log-log plot. So it looks like this guy. We want to know how much is out here, which really doesn't look like much. But there's room. That's why it's called a fat tail. It's got some room out there. There's not much under an e to the minus x squared. That thing is just tanking. Okay. All right, so it's going to be this integral. There's a prefactor c. We're just going to replace it with a proportionality sign. And we've got our integral. We've got our DOM of variables here. We're going from x prime equals x to infinity. This is our 1 over x to the gamma, or x to the minus gamma. So it's a little bit of integration. X minus gamma, we integrate that guy. We get minus gamma plus 1. And we have to balance that with a minus gamma plus 1, right? So you differentiate this. The minus gamma plus 1 comes here, wipes this out. And you decrement that, and you get minus gamma. So it's good, right? X squared goes to x cubed over 3. That sort of business. There's a little bit of calculus floats around here and then now. So up to, and the limits are infinity and x. And so gamma is always greater than 1. So when this is evaluated at infinity, this quantity here is negative. Right? So let's say gamma equals 2. We've got a minus 1. So at infinity, so this thing is a 0. Yep. So it's the bottom one that holds on, and we're going to just put in this is a constant. We're just going to replace that again with a proportionality. X to the minus gamma plus 1. So this little argument says this exceedance probability, the probability that your quantity is greater than some x, also follows, so this is the big deal. It follows a power law, as we saw from those plots earlier on. It follows a power law, and the exponent has gone from minus gamma to minus gamma plus 1. So it's actually moved it up like that. And that process, working with the data, smooths it out. We had that kind of thing that sort of got a little speckled towards the end. It's an integration. Integration cleans things up. Differentiation makes it messy. Integration cleans it up, integrates it. And you get this. So what we do is we work with that power law, we get this exponent, and then we take a 1 off it. That's exciting, isn't it? Yeah. So that's a tiny little calculation, and it's actually how a lot of these things are done. Okay, so when the tail does this, we're fine. We have this nice result. Increases the exponent by 1, and it's good for cleaning up the data. So this is, right, I showed you these before. It's again for the Brown corpus. Here's the raw data, and here it is as the complementary cumulative distribution. So that's probably, I'll add one more piece, and then we'll be done. So putting a straight line through this, bit of a mess, right? Bit nasty, there's some stuff out here. Much better, and then you can talk about what the underlying distribution is. So that's a very nice thing. Discrete variable, same kind of business, but now we have to, instead of we're doing an integral, we're doing a sum. And we don't care too much about it, so we'll make a bit of a mess. You turn these sums into integrals anyway. Just do the same kind of thing. So we'll get to that as well. But you basically use an integral approximation. Same business applies. If this is a x to the minus gamma, you get a k to the minus gamma, you get k to the minus gamma plus 1. All right. Okay, good. So that's a good place to stop. They're weird things. They're messy things. They're everywhere. And lots of shock and surprise in these things. So, and I'll give you a problem set to work on. That's exciting, isn't it? Yeah. Okay.